Hey everyone, I hope you're ready for our last lecture. We're going to introduce random vectors. These are vectors whose components, each of their components is a random variable. And so you can think of the vector itself as some sort of a random object. And we're going to talk about how do you deal with that? What is the meaning of things like expected values and variances and independence? Is there some way that independence can be talked about between the various different components of these random vectors? And we're going to build variance-covariance matrix. It should be a nice ending to the class, giving some insights about a lot of the things you'll be able to do in the future in your future classes. All right, let's get started. This is a bonus lecture of sorts. It's not examinable. The material you see today is not examinable. We're not going to have any example problems that go along with this material, but it's sort of meant to be kind of fun to see how this material will blend with other subjects you'll be seeing, and to kind of get you motivated to see some of the kind of interesting relationships that you'll find as you start to put the various subjects together. So with that said, I'll just go ahead and get started. The subject of today's lecture is random vectors and similar quantities. So let me first say what I mean by that. So random vectors. So for us, a random vector is going to be what you get when you take a sequence of random variables and set and line them up, or kind of treat them as if they're components of a column vector. So we'll just make a definition like that. So here's our definition, sort of a formal definition of random vector. I think that the lecture notes themselves don't use formal definitions in these sections, but they probably should. So we'll say if you have a sequence of random variables, so if random variables, and I'll just name them like x1, x2, and then so on, and let's just say it stops at xn. Xn could be quite large. Like these could be many different measurements from a large population, or it could be a time series or something like that where the index represents time, where you measure one thing over and over again. Let's suppose, so what the idea is, you want to treat these, if these are treated as the components of a vector, as components of a vector, and let's just say it's a column vector, right? And so I'll use the notation, I think this is maybe a physics style notation or maybe an American style, where you put an arrow over the top of a thing to indicate that it's a vector. So if we line them up as a column vector, like this, and then sometimes I'll use curved brackets here, sometimes I'll use square ones. Then this thing, x with an arrow over it, is called a random vector. Right? And so I'll highlight this, that's the thing we're defining. All right, and so we're going to construct a bunch of different operations based on the things we've already seen for this random vector, and others like it. So the first thing I'm gonna define is what is the expectation value for this vector. So I think this is actually given a whole section in the notes, so we'll give it that. And again, I don't think that the notes use a formal definition here, but I will sort of make one up. right? So here's our definition of expectation value. So the expectation value of a random vector is what we want to define. And we're just going to define it so that it's the expectation, it's a vector of expectation values. Expectation value. And maybe you would want to call it just expectation, I don't know, of a random vector. And I may as well just copy it. We're going to use the same one. Is the following. It's another vector, so it's going to be written like this. The output of that is a vector itself, and it looks like this. mu1, mu2, down to mu(n), where each of these mu's, mu I, is the expected value of x sub I. All right, so that's going to be our definition of the expectation value of a vector. And there are certain things that follow from that, and some of the things we'll work on will prove, some we won't. So it follows that if you multiply this by a matrix, so if A is a real matrix, meaning full of real numbers, then you have another vector B, and if that's another, so we'll say it's M by, actually I want to be a little more specific here, sorry. With dimension M by N, and then we'll say B is an M by 1 vector. Then the following is true based on this definition of expected value. And here I'm using the same x as above. So the expected value of this linear combination, the matrix A times the vector x, and then plus the vector b, this is actually equal to A times the expected value of the vector plus b. And so we won't prove that. So let's say proof omitted. You can work on that. We'll omit a lot of the proofs today. Again, it's a bonus lecture of sorts. Kind of more as a taste of things to come. That's sort of the spirit of it. And now just as a reminder, I'm not sure how much you've been working with matrices lately, so I'm just going to remind you of a couple of different rules that we'll use. So this is sort of an aside or reminder. Depending on, I don't know, for some of you it's an aside, for some of you it's a reminder. So these are just some matrix operations. I'm going to introduce only two, really. Matrix multiplication and transpose. So multiplication it's going to work like this. So this is one of the side items. So let's say you have a matrix A, And I'm going to use this kind of notation a lot. So let's say you can write that matrix like this. So in parentheses represents like the parentheses of the large matrix itself. And then here I'll write Aij. These are all of the components of the matrix, or elements of the matrix. And here I represents the row, and J represents the column. That's the standard notation. So let's say that this is a matrix with dimensions m by q. And then let's say you have B, which is another matrix, and let's say it's and its components look like it's like Bij. Sometimes you'll see people, when they want to refer to the elements of the matrix, they'll use a lowercase letter. So I use lowercase b or lowercase a. I'm not going to use that notation. And so let's suppose that's a Q by N matrix. Right, so A has arbitrary, well, A and B don't have the same dimensions necessarily, but the number of columns in A is equal to the number of rows in B. Then if we make this third matrix, which is the product of the two, and it's going to have elements that we'll call Cij, this thing will then be an M by N matrix. And it's defined in the following way, so that Cij is equal to a sum over an index we'll call k. It goes from 1 to, sorry, it should be q. And then it's Aik Bkj. Okay, so that's how you define matrix multiplication, or that's how we're going to define it. The other operation with matrices that we'll use a little bit is transpose. And so this operation, you can also think of this as how you define multiplying a vector by a matrix or vice versa, where the vector is just a matrix that has either only one row or one column, depending on if it's a column vector or a row vector. So you can use this same rule for how to do multiplication with those. So the other operation I'm going to use is called the transpose. And we'll state it like this. So suppose you have a matrix A that's M by N. And then I'm just going to introduce a little bit more notation with this. So we'll say, you can write the matrix like this. You can say A is equal to, this is how I was just doing above, it's equal to the collection of elements Aij. And you can say the following also, you can say the ij element of A is equal to Aij. So that kind of notation I'll use kind of frequently. I think in the notes you'll find these things put into words more frequently. But I think it's easy to understand kind of that, like in particular that this refers to, the thing on the left is saying, I want to talk about row I, column j of whatever it is that's in parentheses. Usually it's not such a simple object that's in there, and that's why you're using this notation. Okay, anyway, so that's some notation we'll use. So the transpose of a matrix A is written like this, A with a superscript of capital T. And so this is called the transpose of A. And it has dimensions n by m. And we'll say the following. So row I, column j of the transpose of A is equal to row j, column I of A. So in other words, the rows and columns are swapped. and A transpose is then an n by m matrix. And you can also see here the transpose of a row vector is a column vector, and the transpose of a column vector is a row vector. Okay, we're going to use those operations a little bit, mostly the transpose. Hopefully that's not too new to you and sort of mostly just a reminder. All right, and so now I want to define something kind of like the variance, but for a random vector. So we'll call this, it's going to make a matrix, so we'll call this the variance-covariance matrix. And the name will become clear, I think. Variance-covariance matrix. It's produced from a vector. Right, so here's the definition here. So we'll say if x is an n by 1 random vector, right, so that's a column with n rows, then the variance of x is a matrix, and it's a matrix that looks like this. Its ij element is the covariance of xi, xj. Right, and so let's write that out so you can sort of see what are its different pieces. So I'm just going to write out the elements explicitly. So the element in the top left is going to be the covariance of x1 and x1, which is also just the variance of x1, hence the name variance-covariance. Then we've got covariance of x1 and x2, and so on up to the covariance of x1 and xn. Right, so that's what the first row looks like. And the second row looks just like that, so I'll copy it. Except that the first index is going to be a 2. Right, so let me go and fix that because this is now row 2. Everything else is the same. Right, and then this just carries on. And then I guess you do like this until you get to the bottom row. And we'll paste again. And everything is the same once again, except we're now at row n. Right? So that's what this matrix looks like. And so notice, so this is an n by n matrix. And we will, if you were to write these out, you probably wouldn't write this as the covariance of x1, x1, and these things on the diagonal, right? Each of these things on the diagonal are actually just variance. So that's variance of x1, variance of x2, and variance of xn, because the covariance of two identical things is their variance. All right, so let's just say a couple of things. So a couple of comments about this. So notice this variance-covariance matrix, which people often just call either the covariance matrix or the variance. People get pretty wishy-washy with the names for some of these things. You'll hear them used differently in different places, so you should be a little careful with expecting everyone to be using exactly the same definitions as you. But so this variance-covariance matrix, so it's an n by n square matrix. It's important that it's square. That's useful for it allows it to have properties like have an inverse and stuff. It's very important to have a square matrix for various different things. And also it's symmetric. That is to say, how do I want to write this? All right, variance of x row I column j is equal to the variance of x row j column I. Right, you should see that it's here. Like, in other words, this thing is the same as this. The covariance of x2 and x1 is the same as the covariance of x1 and x2. So this matrix is symmetric. That also, another way to say that is, or rather, it's equal to its transpose. So transposing it doesn't actually change it. So the third property I want to point out is that the diagonal elements are just variances. So I've already pointed this out, but so variance of x row I column I, so these are the diagonal elements. This is actually equal to, so it's by definition it's the covariance I of xi and xi, which is also the same thing as the variance of xi. So here you can see a little bit of a danger with the notation. This symbol looks a lot, that expression looks a lot like this expression, but they're quite different just by this little thing here, the vector symbol for the argument x. So I guess maybe I'll make it more visible here. The thing over here on the left, this is actually a matrix, whereas this is just a number. Okay, and then the fourth property, if you have a whole bunch of random variables that are, if they're all independent, rather, that's what we already had a whole bunch. So if the components of the random vector are independent, so x1, x2, up to xn, if all of these were independent, if that's true, then all of their covariances are 0. Their variances aren't 0, but their covariances are 0. So if that's true, then this variance-covariance matrix is actually just a diagonal matrix, which we write like this. Diag, and then you put the things that are along the diagonal. Then up to n. Right? Okay, so those are just some properties of the variance-covariance matrix that I wanted to say. That there's a lot of useful things to do with this matrix. In fact, a lot of statistical analysis starts out right away by creating this matrix. All right, and so now I'm going to make a claim that I will prove this one, yeah. So claim that you can express this variance-covariance matrix in a simpler way. It's equal to the expectation value of two vectors multiplied by each other, or a vector multiplied by its own transpose. So this is the vector, the random vector x minus its mean vector multiplied by its own transpose. So that gives you a matrix. And the expected value of that matrix is the variance-covariance matrix. Now here, we'll do a little proof, but in order for the proof to work, we're going to have to make use of something that borrows from or extends kind of the definition of expected value. Here we're going to say, just like we did for a random vector, the expected value of a random vector is a vector of the expected value of its elements. We're going to do the same thing for a matrix. We're going to say the expected value of a matrix is the matrix of expected values of the elements of the matrix. So that will come up in the little proof. This proof, I'm going to write it a little bit differently than the notes. You might prefer the version of the notes where things are kind of written out more explicitly and take a lot more space. I thought I would try to do something slightly different. So we'll say I'm going to do it by looking at the elements of the variance-covariance matrix at first. So row I, column j of that matrix, by definition, that's the covariance of xi and xj. Right? And that then is the expectation value from our previous lecture of xi minus mu I times xj minus mu j. Right? And then we're going to use that rule I mentioned. So then if the expected value of a matrix, if row I column j of that is equal to the expected value of row I column j of the matrix, I think they don't bother to make that rule in the notes, but it's needed. We have the following. So let's say I invent a matrix that I call V, and that's the variance, or rather, so this is the expected value. If I say it's the expected value of some matrix V, right, then if you look up here, so this is Vij, then xj minus mu j. Right? Now that thing can be written in a sort of a funny way. You can write it like this. This is sort of silly, but write it as a sum with one term. K equals 1 to 1. And we'll write this as x minus mu row I column k. Right? So this is really a k, it's a column vector, so it's row I column 1. And then we'll write this again as x minus mu, the second term, as row j column k. So again, that's a column vector. That's the same thing. So I'm just going to copy this. Except I can swap these two, j and k, if I make this the transpose. Right? Now if that's true, then this is actually a product, a matrix product. So this is from the definition of matrix multiplication. Right? This is row I column j of that product. So having a sum go from 1 to 1 is a little bit silly there, but I just want to make it look a lot like matrix multiplication so you can see how that came about. And so this tells us then that the matrix V is equal to, right, so if it's element ij of v is element ij of this, then that thing that I just underlined is v. And that's what we were trying to prove, that the variance-covariance matrix was the expected value of that. Okay? Alright, so let's try a little example. We're going to use repeatedly some stuff from the previous examples once again, the never-ending examples. So here's our little example. And we're going to try to compute the variance-covariance matrix for a simple case. So let's say let the random vector z be equal to, and so it's going to have two components, z1 and z2, where z1 is equal to x and z2 is equal to y. These are the two random variables that we were using in our many previous examples. So x and y are from previous examples. I think in the last two lectures. So I only want to use this because we know the variance of x and variance of y and the covariance of x and y. We've calculated those in the previous lectures, and so I'm going to make use of those. And so what I want to do is I want to find the variance-covariance matrix of z, right? And so it's 2 by 2, and it looks like this. So it's covariance of z1 and z1. So that's the variance of x, and the covariance of z1 and z2. So that's the covariance of x and y. And then these are repeated. Right, and so what this translates to is the variance of x and then the covariance of x and y. And then this is the covariance of, you could write y and x, but it's also the same as x and y. And then the variance of y. And these are things that we calculated in the previous lectures. They're rather hideous, but I'll write down their answers if you really wanted to get numerical answers for these. So this is a matrix, and it's got these components. They are 71 over 225 minus 1/25. And so then this repeats, symmetric. And 33 over 50. So again, these are from previous lectures. I think if you look in the last lecture, I think that's when we calculated all three of those numbers. All right, so that's how you would compute the 2 by 2 variance-covariance matrix for this random vector that has two elements. All right, and now we're going to kind of work our way towards a more interesting rule. We're first going to state it in a kind of a clumsy way, and then we're going to tidy it up a bit and make it a little better. So we're going to talk about the covariance of linear combinations. Of random vectors. Or rather, of random variables. Okay, so this is going to be we're going to start with a claim. So claim if you have these random variables that we've been using, x1 up to xn, if these guys are random variables, And then let's suppose you have constants. I'll call AI and BI. These are real numbers. So I is equal to 1 to up to n. So you have two n constants. Some of them are a's and some of them are b's. Then the following is true. It's kind of a long statement, so maybe I'll skip the line break here. So we're going to say the covariance of, and then we'll write this out, A1 x1 plus A2 x2, and so on, up to AN xn. The covariance of that vector, or sorry, that random number, sorry, the covariance of that random variable, which is a linear combination of lots of random variables, and then another, which is the sum of the same, of another linear combination of the same. Like this. This thing is equal to, and it's going to take enough space that I'm going to put it on a separate line. It's not huge, but so it's equal to the following. It's a sum I equaling 1 to n, and the same for j, of AI bj, and then the covariance of xi xj. Right, so that's kind of a mouthful, so let's take a look at what it's saying once again. So this is saying this expression on the right, which is somewhat interesting looking, is the covariance of two random variables. Here's one of them. It's a linear combination of this sequence of random variables. And then the other random variable is a different linear combination of those same random variables. Right? So that's how that looks. And then we will not prove this, so this proof is omitted. These are fun things to try to prove. Not all like challenging necessarily, but just things to do if you want some fun things to do over winter break. Over the holidays when people are talking, you can break out this one. Okay, so let's try a little example, see how you can actually use this thing for a simple case. Alright, so let's say use those same x and y. From the previous examples. Right, from the last two lectures. I want to calculate, and then we'll just write it and then we'll do it in the same line. The covariance of 2x plus 3y with 4x plus 2y. Right? So following the statement up above, right? So this is a linear combination. You had two different random variables, x1 and x2. So x1 is x and x2 is y. And so one linear combination is 2x plus 3y, and the other one is 4x plus 2y. And so we want to find the covariance of those two random variables. And so it's equal to, we're going to have two different sums, right? I goes from 1 to 2, and j goes from 1 to 2. And then we're going to have the different constants that were used in the linear combinations, and then the covariances. Right, so that's how that's going to look. I guess I'll leave that up there while we do this. And so this is going to look like, let's go through these in order. So it's 2 times 4 times the covariance of x and x. In other words, the variance of x. Plus, and then the next term would be 2 times 2 times the covariance of x and y. And then we have plus 3 times 4 times, again, the covariance of y and x, which is the same as the covariance of x and y, plus, and lastly, 3 times 2, the covariance of y and y. All right, and so we can write that more simply as, let's see, so we have 8 times the variance of x. Right, so that's this term here. Then I'm going to put this term here, which is 6 times the variance of y. And then there's two different terms that are written that are these are the same. The covariance of y and x is the same as the covariance of x and y. So I've got 4 plus 12. Yeah. Okay. And then in our desperate attempt to actually give you numbers to come out of this, you can look at the previous examples again and find, or just the one previous example above, and you can find the variance of x and y, and then the covariance of x with y, and you get the following. So this becomes 8 times 71 over 225 plus 16 times minus 1 over 25 plus 6 times 33 over 50. I just find these kind of entertaining, these silly looking rational numbers. Like, why do you just write a decimal? Why don't you do that? I don't know. And so that, well, here's the reason why, because it comes out cleanly in the end. So it's 263 over 45, if you call that clean, or approximately 5.8. Maybe it's all just to avoid approximations. Probably is. Okay. So you can write these, you can do this whole thing in a more, so the whole motivation of this is a sort of an interesting rule, this thing here. It's a bit of a mouthful, but we can write it in a better way, particularly like, look at all this mess. So this linear combination is really like a dot product of two vectors, and that's true of this as well. And so we're going to try to write this in a simpler way, and then we'll try to use the rule in the simpler form. So this can be written more cleanly. So it can do this. I don't know, more cleanly? Is that an expression? It is now. Or maybe I should put this in quotes. Right, so let's do the following. So let A be a vector, column vector, A1, A2, AN, and B also made out of those constants, B1, B2, down to Bn. Right, so if we do that, then those long arguments up here, so this is A dotted with X, and this is B dotted with X, or if you want, you can write them in terms of transposes and stuff, which is what we'll do. We'll do both, I guess. So A1, X1 plus A2, X2, and so on. AN, XN. This is equal to A transpose, the transpose of the vector A times the vector X, which is another way to write just the inner product or the dot product of A and X. Right? And similarly, B1, X1. Bn, Xn. This is also another similar product. Like that. Okay. then we can restate our rule in a little bit of a simpler way. And we're going to, so the left-hand side of the rule is now going to be a little more tidy, but we're also going to tidy up the right-hand side. And so then our rule, or our claim, which we didn't prove anyways, can be rewritten. Or maybe you want to say simplified. But it's a bit of a long journey, but it's nice at the end. So we've got, on the left-hand side, we've got the covariance of A transpose times X, B transpose times X. Or you can write dot products there if you like. And then the right-hand side is not, we're going to mess with the right-hand side. We're going to try to make it look better, but it started out like this. I equals 1 to n, a sum, and then the same for j. And we've got ai, b sub j, and then this covariance. Right? Now I'm going to rewrite this as, put the a sum on the outside, and then, sorry, the I sum, if you want to say it that way, the j sum on the inside. And then we'll put the b terms on the very outside edge. So this looks a little bit like, trying to kind of make something look a little bit like matrix multiplication. All right, and now how does that? Let's just really expand that. So we'll expand the a sum. So this is a1 times all this stuff with I equals 1. Right. So we'll do that. Oops. Like so, right? Plus, I'm going to move all this really far to the left. So let's get all this stuff over here. Oops. Going to need a lot of space. I think I've still got that thing copied, I hope. So then there's a2 times that sum again, but with I equals 2. Right? And then that keeps on going. So that's how this looks when you expand it out. an, and then here the I is equal to n. Right? Now, if you stare at that long enough, you should be able to see this looks like another kind of dot product of two vectors. So here's a1, a2, an, and here's component 1 of some vector, component 2 of some vector, and component n of some vector. And so we can write that in sort of really hideously long form as a1, a2, an, which this is the transpose of the vector of the column vector a multiplied by sorry about that. So let's paste them in. Oops. Like that. And now I'm going to make this a vector. Right, and so each one of these was one of the components of this vector given by the I index. So 1, 2, up to n. Okay. Hope that's somewhat clear how we got that. And that each one of these vectors, right, this is another dot product looking thing, right, summed over j. So here's component j of b and component j of this other thing. And then this is the same, but for the 2 guy, and so on. And so this whole thing can be written as, so the A is over here. I may as well just write that as A transpose because I now recognize what it is. A transpose, and then times this big matrix, right? So these are, I'm expressing each one of these as a dot product now. And so this is one of the pieces. These are the components of one of the vectors, which look familiar, the covariance, variance-covariance matrix. And then these are the others, the B vector. And so this is going to look like this. Covariance. So this is the variance-covariance matrix. Oops, that's x1. Right, and then I'm going to copy that because each line looks like that, but with the row changed. Right, so now we'll change the row markers. You can really build things up fast when copying and pasting. So this is row 2, and this is row n. Right, so that's the variance-covariance matrix, and then these things are multiplying the components of the vector b, and so we'll write it like this: b1, b2, bn. Whew, that's a lot to write out. And so you can write this very succinctly as A transpose, so that we already saw. Then this middle thing, the big matrix, that's the variance-covariance matrix. And this thing on the right is the vector B, the column vector B. So that's a really clean and tidy way to write that the rule that we had before. It's much simpler. It's still a little bit involved, but much simpler than what we had. So in other words, I'll summarize all that chatter with what we've just found is that the covariance of these two random variables is equal to this funny expression. So A transpose variance-covariance matrix of X, and then times the vector B. So that's a rather tidy rule in the end, or at least it's much tidier than it was when we started out. So remember this expression here, this is the equivalent of way up here. Where's that long thing? The thing that was so long it took up 2 lines. This thing. Those are the same statements, but that last one is much easier to look at. It's still a bit of a mess, but it's just better. All right, and so let's try it out. So we're going to do the exact same example, just calculating exactly the same thing we did in the last example, but using this new version of the rule. So we'll do an example. So redo the last example. Using the new version. of the claim. Now the result, of course, is the same. And it's not going to look hugely better to do because this is only, we're only dealing with two random variables to make our vector. So our vectors have only two components, but still it's a little cleaner. So we've got A, the vector A is going to be, so if you look back, where's that last example? Let me find you. It was here, right? So there's the components of the vector A are 2 and 3, and the components of the vector B are 4 and 2, and these guys are going to make up our random vector. So we'll put those together. So A is going to be 2 and 3. B is going to be 4 and 2. And then the random vector, which we'll call Z, is X and Y. Now I think this is the kind of thing where seeing this done with a two-dimensional case is not that extreme. If you have a much higher dimensional, many components to your random vectors, to your random vector Z, this becomes more powerful. But okay, so the idea is we want to compute on the left-hand side the covariance of 2x plus 3y and 4x plus 2y. Right, so that's just equal to the covariance of A transpose times Z and B transpose times Z. And that's equal to, according to the rule up there, A transpose times the variance-covariance of Z times B. Right, so we'll write that A transpose. So this is, I'm looking at the line up here to see that. Times variance-covariance matrix of Z times B. Okay, now we can fill those in and you just get a little matrix multiplication problem. 2, 3, that's A transpose. And then this somewhat hideous variance-covariance matrix, 71 over 225, 33 over 50, and the off diagonals are minus 1 over 25. And then the vector B, 4, 2. Now here, we can go ahead and write this out, what it comes out to cleanly, but I think honestly if you were at this stage and you wanted to check if this were right, and if you had some kind of tool that allowed you to do matrix multiplication in a computer, you just put those in and check that they gave you, what was it, 0.58 or something like that. Yeah, or 5.8. But you can do the arithmetic carefully and you get the clean answer. So this becomes, so let's multiply this vector, this row vector and this matrix. So we'll do that first. And then we're going to get another row vector. And that turns out to be, I don't do it this fast in my head, but I'm just telling you what it turns out to be. It's 23 over 45. It's the first component. And then 19 tenths. Right? And then we've still got this vector 4, 2. And if you put those guys through there, you get, and then you do this dot product, or however you want to call it, matrix product, you get 263, you get the expected answer, 45, or rather 5.8. That's what it is, right? 5.8. I lost track. Go back there, way back there, yeah. It comes out right, is what I was trying to say. Yeah, so that's a cleaner way, that's a simpler way to do it, just like that. All right, so there's other kind of fun and kind of cool relationships here, but we're not going to prove them, just going to kind of claim them. So some other cool relationships, I think they're cool. Proofs omitted. These are fun because some of them kind of look like you would expect, but everything is somehow, where you had scalars, everything's are made into a vector and a matrix, and products involve transposes and stuff, and it's kind of neat to see how they turn out. If you look at the variance of just A transpose times X, right, so that's a linear combination of X's. So we actually saw something like this with regular variances. I don't know if you remember, so this is like the variance of a constant times X. I don't know if you remember what that was, but that turned out to be A squared times the variance of X. And so in this case, this turns out to be A transpose times the variance-covariance matrix of the vector X times the matrix A. Or sorry, the vector A. So these two guys kind of replace the A squared, and this, which was a number, is now this variance-covariance matrix. But in the end, you put these three things together, and you do just get one number out of that, the variance of this linear combination of the components of the random vector X. So I think that one's kind of neat. It's kind of cool looking. And then another, so also for a square matrix, n by n matrix A, then the following is true. The variance of A times the vector X is equal to the matrix A times the variance of the variance covariance of the vector X times the transpose of A. So that's a similar statement, but involving matrices. That is to say, this thing is the variance-covariance matrix. Instead of just the variance of a random variable. Okay. So those are I think those are sort of fun and kind of cool looking things. So, and again, we're not proving those. You can try to prove those over the holidays as entertainment. I think it's good entertainment. Okay, so now we'll get on to our very last thing that we're going to talk about, which is this is sort of an interesting, it's really just definitions, but they're kind of cool definitions, and you can kind of see why they're useful. We've talked about the covariance of two random variables, and we want to introduce the covariance of two random vectors, right? So we'll call it, and that has a name. Covariance of two random vectors. It's called the cross-covariance. To remind you that, I don't know, somehow that they're random vectors that are being covarianced. Right, so we're just going to define this. I think it's kind of cool. You can sort of see how it could be useful. So remember, when you look at the covariance of two random variables, you're trying to find out how dependent they are. And you can imagine if you have two random vectors, you might want to ask that same question: how dependent are these two random vectors? And so this is a way to answer that. So we'll say, let's say you have X is a random vector. Let's say it's n by 1. And let's say its means look like this. So the expected value of the vector X is equal to, I'll write it like this, mu sub X. And then similarly, if y is another random vector, but different dimensions, m by 1, and its means look similar. Right? Then they're cross-covariance. Cross-covariance. So this is some measure of how dependent they are, or how independent they are, of x and y, the random vectors x and y. Sorry, that's making a bit of mess. Is the following. So we write it like this. We write it as the usual covariance notation, but then we put two vectors in its argument. And this looks like the following. It's the expected value of this product, x minus mu x. So this is called centering. When you subtract the means, so this is the centered version of x, of the random vector x, times the transpose of the centered version of y. Right? So this argument inside here is a matrix expected value. So this gives you a cross-covariance matrix. So this thing is an n by m matrix with ij element, we'll write it as covariance x and vector y, and this is equal to the covariance of xi and yi. So that's kind of cool. I guess we're going to finish with one more thing, a claim, not a definition. So we made that definition, and then we'll just make a claim about some way to use this. So claim, this is our last little thingy, and we're going to omit the proof. More holiday entertainment here, endless holiday entertainment. This will get you through between semesters, so you can get back into the books afterwards. We'll say, so here's the claim. Let's suppose you have m equals n in the above. If in above m is equal to n, so in other words, the two vectors x and y have the same dimensions, same length, then the variance of the sum of the two random vectors x plus y. Right, so this is the variance-covariance matrix of one random vector, and that random vector is the sum of x and y. That turns out to look like the following. It's the variance-covariance matrix of the random vector x. Plus the variance-covariance matrix of the random vector y. And you can do this sum because they had the same dimensions. Plus the cross-covariance of x and y, plus the cross-covariance of y and x. Now those are not the same. And I think you can see that if you go back up here. Right, if you see what the cross-covariance looks like, it's this vector times the transpose of this. if you switch the arguments x and y, what you end up doing is taking the transpose of this whole thing. So it's not exactly the same. So it's kind of an interesting expression. So I'll just finish with a little statement. So there's lots of other fun things to find. Lots more similar things. So for example, a very obvious thing that you might want to introduce, and I won't introduce it, but I'll just sort of describe it crudely. Remember, this thing, the cross-covariance, is some measure of how dependent x and y are, but it's a pretty flawed measure because it depends on the units of x and y. If you change the units of x or the units of y, you'll change this thing, just like you would for the covariance of two random variables. And so as you might not be surprised, there's a thing called the cross-correlation. I don't know if it has two L's or not. It does today. So there's a cross-correlation. I think it only has one. Let's get rid of that. Of x and y, which we won't define, but you can kind of imagine what it might look like. It's somehow normal scaled by variance-covariance matrices. Well, you've done it. You've come to the end of all of our lectures. I hope you've had a good semester. I hope you feel like you've learned some new things. I hope you feel like this last lecture on random vectors was kind of enticing, maybe a little encouraging you to look further into the subject. And I hope you've enjoyed yourself. Bye!